I've been working in IBM for quite a long time. And when I started in IBM, I did J2EE development and I did messaging. But then I fairly quickly moved to the Java Technology Centre, which is in the UK. And in the Java Technology Centre, we developed the IBM JVM. And now, I don't know how many of you use it, but it really is a superb JVM. And one of the ways in which it's so good is its performance. And so I worked for many years on improving the performance of the JVM. In order to get such good performance, we do have a large team who work quite hard. And this was all C development. And after a few years of that, I thought, well, I work in the Java Technology Centre, and I think I'd actually rather do Java development. And so I moved to working on Java performance tools instead. And so instead of improving the performance of our JVM, I helped customers improve the performance of their Java applications. But in both cases, what I found was that the more I learned about performance, the more it continued to surprise me. And the more times I found things which were just utterly baffling about the performance of an application. And the more examples of things I found which were really quite counterintuitive. And so I'm going to start by talking about general principles of how you should develop for performance and how you should think about performance as a Java developer. I'm then going to move on to a few concrete examples of some fairly simple things that everybody thinks are true that really aren't true. And then I'm going to spend quite a long time talking about garbage collection. And this is partly because I know quite a lot about garbage collection. But it's also because garbage collection is one of the biggest areas for performance myths. And finally, I'm going to talk a bit about compilation and how that relates to Java performance. And then finally, I'm going to talk about Java performance as a whole. So I've got quite a few myths that I'm going to talk about. And the first myth is, I should take performance advice. Now, I think probably you're sat here in a performance talk in which I'm giving you performance advice. And so it seems natural that you should want to take the performance advice. And like I said, performance is really quite complex. And no one person can know it all. And it's really natural that as you're developing your application, you want to look to others and you want to look to experts for performance advice. And you read on the web or you read in a book and it says, oh, you should do this. This is your performance best practice. And you go away and you think, oh, I'm going to make my application so much better and faster and everybody's going to be really pleased. And you take all your code and you go away and you replace this with that and you think, oh, yay. And sometimes this is a good thing to do, but sometimes it's actually not a good thing to do. And the reason is that there really are no universal performance truths. And the reason for this is that every application is different, and hardware changes, and virtual machine technologies change. And so something which was perfectly true 5 years ago can now be the exact opposite of true. But it also depends on your application. And every application is different. And something which will give a good performance enhancement to one application can actually have a terrible performance effect on another application. And so the only way to actually be sure whether what you're doing is going to help your performance is to measure. So you have to measure before you make the change, and you have to measure after you make the change. Hopefully, you'll see that you improved your application performance. Sometimes you'll see that even though you did something that everybody knows is good for performance, you actually worsened your application performance. And in those cases, you have to go away and undo your change. So, how do you measure performance? Well, it's easy to think, I can measure performance without defining performance requirements. Because everybody knows what performance is, right? It goes faster or it goes slower. And so, it's tempting to, instead of actually laying out in a sort of a project management way, this is my performance requirement, I'm going to do 10 transactions per second, you say, I'll just use some performance tools. After all, performance tools have performance in the name, right? They must be for measuring performance. And so you look at your garbage collection, you look at your verbose GC, and from your pause times, you try and figure out whether your application's going fast. Or you look at a profile, and you see that how much time you're spending in this method has, it used to be 20%, and now it's 10%, so you think, oh, excellent, my application's clearly going faster. Well, that's not actually true necessarily. When you think about performance, it has to be based on your performance criteria. The performance tool cannot do your performance measurement for you. It can give you guidance on how to improve performance. It can tell you where your bottlenecks are. It can give you suggestions about what things you might want to try and change, but it can't actually tell you whether your application is going fast enough for you or not. And so you have to base your performance measurement on your application and your quality of service requirements. So you think about what they are. Are they throughput? Do I just want to get as many transactions through as I can? Or is it perhaps more response times? And then, if it's a response time criteria that you have, what kind of response time criteria is it? Is it the mean response time? And that's actually quite similar to throughput. Or is it perhaps the 90th percentile response time? So what that means is I want 90% of my transactions, to have a response time of 100 milliseconds, but a few that are outside that's fine. And if it's an interactive application or an application that has a user sitting somewhere, that 90th percentile is usually the most useful criteria. 90th percentile is what users perceive in terms of performance. So if 90% of the transactions meet your quality of service requirement, then the user is going to be happy. But sometimes it's not actually a user that's at the other end. So sometimes what's important is the worst case response time. So for example, if you've got Java flying your plane, then getting it right 90% of the time isn't really going to be good enough as your plane crashes into the mountain because you didn't meet the response time criteria. So sometimes it really is, it's the worst case which is important. But one of the things I hear a lot when we talk about performance is that I want to measure performance, but my application's really quite complex. It's spread across 4 servers. To try and create the test environment in order to measure performance, it's just too hard. I need too many boxes. I need too much hardware. The setup takes a week. And so then you think about benchmarks, and you think, well, what is a benchmark? A benchmark is a standardized application, and the whole point of a benchmark is to try and measure and communicate about performance. And so you think, instead of measuring my application, which is really hard, I'm just going to measure this benchmark, which is quite easy. And of course, it's a benchmark. It's exactly designed to measure performance. So this is good enough, right? Well, no. Because application performance is sensitive to so many factors, so it's sensitive to the application load, it's sensitive to how fast you allocate objects, it's sensitive to how those objects talk to each other. Sometimes something which is completely true for a benchmark will actually be completely wrong for your application. And so you really can't use benchmarks to guide your tuning decisions. So how many of you have done science degrees? A good number. And how many of you have done C development? Right, I've done both of these as well. And in fact, everything in these slides, these are all mistakes that I've made. It's not that me sitting here going, I know everything, because these are all painful lessons I've learned. And one of the painful lessons I've learned is about micro benchmarks. When you have a scientific background, you think, I want to know whether something's true or not. I'm going to measure it. And in order to measure it accurately, what I'm going to do is I'm going to isolate the other factors. And so say I want to know if in my application I should use string builder or string buffer, say. I want to know which is going to be best. Instead of running my whole huge 4-day setup application, I'll just write a tiny little application, run it with string buffer, run it with string builder. I'll see which is fastest, and then I'll know that I've done a really good, accurate, objective measurement. Unfortunately, in Java, it doesn't actually work that way. Because what you actually care about is the performance of your whole application. Isolating some of those things is going to give you a misleading answer. In C, when you isolated other things, in general, you did get the right answer. But because Java has the JIT, and it's got the garbage collection, and it's got a quite complex threading model, when you take those things out and try and measure just one thing, sometimes you get an answer which is the opposite of correct. So again, do measure your actual application, even if it's hard. So, again, we're all here, we're thinking about performance. We want our application to go faster. And so we think, naturally, speed is good. I should optimize things. But it seems so obvious that, of course, we should optimize things, but this isn't actually true. And there's a few reasons. One of which is that, say I've got an application and it's got two methods, and I'm just sort of looking through it, trying to see inefficiencies. And I've got method A, and I can see, oh, well, I can probably make a 20% performance improvement by, changing a few things. But then I look at method B, and I get really excited because I think, oh, look at the idiot who wrote this. They've done it so inefficiently. I could double the speed of this method if I made some changes. But in my example, method A uses 25% of the time. So, quite a lot of the application time is spent in method A. And method B only uses 2% of the time. So even though, when I see an inefficiency, I want to get rid of it. And the inefficiency in method B is so bad that it's just so tempting to change it. But in fact, for my application, I'm much better off spending my time optimizing method A because that's going to give the bigger difference to the application as a whole. And sometimes it's worse than that, though. Sometimes, if I do an optimization, it's not just that it doesn't make as big a difference as I hoped it would. Sometimes it actually makes things worse. And sometimes when I do the optimization, I'm being good, right? So I do my optimization, I change things, I measure, I confirm, yes, I am a genius, I made performance better. And then a month later, somebody makes some other change, and that just changes the application characteristics a little bit. And then my brilliant performance change actually makes things worse, and it would have been better off if I just hadn't done anything at all. And because things do change, I've got a quote here, which is, the first rule of program optimization is just don't do it. The second rule of program optimization, which is for experts only, is don't do it yet. And what this is trying to get across is that because things are so sensitive, you shouldn't waste time at the beginning of your development cycle trying to optimize things which may not even matter later on. And going back to my example of method A and method B, in an ideal world, perhaps we could optimize both method A and method B. But in fact, we haven't got all that time. We've got development cycles that are tighter than we'd like. We've got managers saying, is it done yet? Is it done yet? And so we do have to be wise in where we spend our optimization time. And this is particularly true because sometimes when we optimize code, you make it less elegant, and in order to make it go a bit faster, you reduce the maintainability of the code. And so it would be really sad if you make your code more fragile, and then in the end you didn't even get a benefit for that change. And so I've got another quote here, which is, we should forget about small efficiencies, say about 97% of the time, which is actually almost all of the time. And it goes on to say, premature optimization is the root of all evil. So from that, you may be thinking, and certainly I have, that premature optimization is the root of all evil. Excellent. I've learned my lesson, I'm not going to optimize, so I can write whatever I like, and then I'll think about optimization at the end of my development cycle, right? Because I'm good, and premature optimization is the root of all evil. Well, no, that's actually not true. You do still need to think about performance at all stages of the development cycle. For example, some inefficiencies are just so obviously inefficient, and they're spread so through the code that trying to get rid of them at the end would be hard. It's better just to code it cleanly all the way through. And so an example of this is hash map versus hash table. Functionally, they're fairly similar, except that one is synchronized and one isn't synchronized. And the synchronized one, there is a performance overhead for that synchronization. And so if you know your code is single-threaded and is always going to be single-threaded, you're better off not using the synchronized one. And certainly when I look at my code, it is filled with hash maps. And so you can, even though each one, the performance impact is pretty small, when you add it over the whole application, it makes a difference. Another example is some things are just such a huge performance overhead. So for example, I/O. Whenever you do I/O in your application, it's probably going to be a performance bottleneck. And so right from when you design your application, you want to think about how can I minimize my I/O? How can I batch my I/O? How can I make sure that I'm doing my I/O efficiently? And when we talk about optimization as the root of all evil, what we mean is that little fine, niggly, fine-tuning pieces of code to maybe change the order in which we do something, or use something a little bit differently to make it, and maybe make less maintainable code but make it faster. And that really isn't the same as designing a scalable architecture, and that you have to think about at the beginning and all the way through, because it's quite difficult to change your architecture once you've got to the end of your development cycle. It's expensive and messy and bad. And so do make performance part of the process. Set up your performance measures early. Say, I care about response times. I want to have this kind of response time. Do measure constantly to make sure that you're on track. Because when you introduce a performance regression, it can be incredibly difficult to try and work out which of the 10 innocent-seeming changes you made suddenly caused your performance to go catastrophic. And so if you measure frequently as part of your nightly build, say, then you just have to sift through a few changes to figure out which was the bad one, and it makes it so much easier. And it also does mean that right from the start of your development cycle, you know that your performance is roughly on track. It may not be your final target, but you know that you're not aiming for a response time of 100 milliseconds when your actual current response time is 2 minutes. So what are some of the things, that's how we think about performance, but what are some of the things that we can actually do to help performance? One of the differences between C and Java, I think a lot of people, when you think about it, you think, well, when I did C development, I spent so much time thinking about memory leaks and thinking about memory management and trying to make sure that I didn't leak memory. Because, of course, a memory leak is very bad for performance. In a long-running application, it will cause the application to crash. Even in a short-running application, it means the performance isn't going to be as good as it should. And so it's so wonderful when you move to Java and you think, oh, isn't it nice that I don't have to think about memory leaks anymore? Because, of course, Java can't have memory leaks. Well, actually, Java can have memory leaks. And I say this because my code leaks memory all the time. And memory leaks happen when, what a memory leak is when an object which is no longer required is still in memory. And there's two kinds of memory leak. The first is when you've got a reference to an object and you need to free that object, but unfortunately you misplace your reference. So you know you need to free this address, but you can't quite remember what that address is, so you've got no hope of freeing it. The other kind is when you hold on to a reference to an object which is no longer in use. And in C, you can get both kinds of memory leak. In Java, you can't get the first kind, but you can still get the second kind. And usually, the solution is reference objects. Now, how many of you are in the habit of using reference objects? A few of you. Quite often, I talk about memory leaks, and I say, who uses reference objects? And no one in the audience raises their hand, which makes me sad, because they're not very often used, but they're so incredibly useful. And what reference objects do is they make the garbage collection a little bit more sophisticated. Because how garbage collection usually works is it's quite a binary thing. So either an object is still referenced, and so the garbage collection doesn't collect it, or it's not referenced and the garbage collection collects it. And what reference objects do is give you slightly more subtle semantics. And so you've got soft references, and what they say is they're useful for objects which are quite difficult to create. So for example, perhaps it's an image file that you've read off the disk, and you'd quite like to cache it in memory, but you could recreate it. So if the memory is needed, you're willing to get rid of it and then recreate it later. And weak references are even more useful for preventing memory leaks. And what they are is a reference which the garbage collector ignores. And so it's extremely handy when you've got something like a listener pattern. And the way listener patterns generally tend to get written is that the thing which sends out the events registers listeners. And usually the listeners forget to unregister themselves. Sometimes because they don't know that they've reached the end of their life. Sometimes just because they forget. And so then you get this poor thing which is driving the events, and it's got this hash map, and it keeps getting filled and filled and filled with all these listeners that aren't actually required anymore, but they're not going to be garbage collected because something's holding on to a reference to them. And so using weak references in this case helps enormously. Another way in which we can fall foul of standard performance thinking is that you think, well, the order in which I do things doesn't matter. I look at an algorithm, and as long as two steps are independent, obviously it doesn't matter which order I do them. And taking the example of traversing an array, going across it by rows should be the same as going across it by columns, right? Because either way, you have to visit every item in the array. Well, actually, that's not true. And the reason for this is that hardware does matter, and in particular, CPU caches matter. And over the last 20 years, the speed of hardware has or the speed of CPUs has increased enormously, and the speed of memory actually hasn't kept up at all. And so it used to be that memory wasn't a particular bottleneck for an application, and now memory is a huge bottleneck for an application. One benchmark measured that 45% of the CPU cycles were just spent waiting for stuff to come back from memory. So you think if you could get rid of that, in that case, you could actually double the performance of your application. And one of the ways most modern hardware tries to deal with the fact that memory is so slow is it uses CPU caches. And so you've got a hierarchy of caches. There's one very close to the CPU, which is extremely fast, but very small. Then there's one above, which is pretty fast and a little bit bigger. And access to something which is already in the cache is much faster than if you have to go all the way out to main RAM. And of course, if you're paging and you have to go all the way out to disk, then you're basically dead as far as performance is concerned. And so when you look at an algorithm and you don't think about the hardware, you just think about the mathematics of how many steps there are, you can actually come up with some quite wrong answers about how your application is going to perform. And so in the example of the arrays, you're actually much better off going across the rows rather than going by the columns, because once you've got the array in memory, accessing the next thing in the array is going to be pretty fast. Whereas if you're going down the columns, you bring the first array into memory, and then you want to go to the next column, so you have to bring the next array into memory. And each time, everything that you're accessing has to be pulled from main memory into the cache, and it's going to be very slow. Another example is when you've got something in memory and you're trying to do a calculation on it. I had something a while ago where I had a huge array of points, and they were two-dimensional points, x and y. And I had two methods, one called getMeanX and one called getMeanY. And in each case, I wasn't completely stupid about it. So when I calculated the mean x, I did cache the mean x, and then unless the data points had changed, when the next call to it, I returned the cached value. But what I hadn't done was when I was calculating the mean x, I never thought to calculate the mean y at the same time. But in fact, in that calculation, it was so worth doing because the cost of going across the array and pulling the whole array into memory was enormous compared to the cost of that little extra calculation for each point, calculating the mean y. And so just on the off chance that after someone called getMeanX, they'd also call getMeanY, it was worth doing both calculations at the same time. And so this brings me to the subject of garbage collection, because garbage collection is quite closely connected to the cache as well. And the first thing I hear about garbage collection a lot of the time is that garbage collection is all about collecting garbage. And now when you look at those words on the slide, you think garbage collection is all about collecting garbage. It has to be true, right? Well, no. I say this so often that I've actually thought of getting a t-shirt printed which says garbage collection is not just about collecting garbage. When we say garbage collection, what we're doing is we're using it as a shorthand for automatic memory management. And that actually is a lot more than just reclaiming unused memory. And memory management, it's got three components. One is the freeing memory, which we think of as garbage collection. But another important part of it is allocating memory. And another important part of it is arranging memory. So garbage collectors often rearrange memory. And all of these are really quite important to the performance of an application. And when you try and understand what garbage collection is doing, and when you try and choose a garbage collection policy, you have to think about all three. And I think this, again, when people come from C backgrounds, or even when they don't, you look at your garbage collection and there's all these pauses, and you've got an interactive application, and you're trying to do something, and the garbage collection is collecting, and so your users aren't getting any feedback because there's this stupid garbage collection, and you think, well, okay, I'm glad I'm not programming in C. I really didn't like having to allocate and free everything by hand. I did always get crashes because I did it wrong, so I'm happy to have the garbage collection, but my application would go so much faster if I didn't have it. But it's actually, sometimes the opposite is true, and garbage collection can make applications go faster. And by this, I really mean faster than it would if you had manual memory management. And GC can provide performance benefits in all of the areas that I talked about earlier. So you can get faster freeing of memory, you can get faster memory allocation, and you can get much faster access to memory. And this isn't me just standing up here and making this up. It's been demonstrated experimentally. So about 14 years ago, a group of people took a C garbage collector, which actually has a lot fewer performance benefits than a Java garbage collector. And they took a whole bunch of normal C Unix programs, and they recompiled them with the garbage collector. And they did, in fact, see a performance hit. So on average, the performance was 21% worse. But considering this was 14 years ago, it was a really primitive garbage collector that they had. You think, well, 21%, it's actually not the disaster that you maybe thought it would be. And also, in the best case, their performance was 9% better with the garbage collector than without. So it certainly, it wasn't guaranteed that garbage collection was going to make the performance worse. And this is even more true for Java. And so a group of people, what they did was they took a JVM and they instrumented it. And so they ran their application and they looked to see where the garbage collector would free an object. And they made a record of all those. And then they took the garbage collector out of the JVM, and instead they put in manual memory calls where their instrumentation told them to. And what they found was that the performance was, in fact, about the same with the manual memory management as it had been with the garbage collection. And again, in the best case, having the garbage collector made it outperform not having the garbage collector by 9%. And you think, okay, well, garbage collection, maybe it's not so bad for performance, but, in C, I could free memory for free. I didn't have a cost for it. And then when you look at garbage collection, what I've got here is I've got a graph of the pause times. And you can see there's all these nasty pauses where my application isn't doing work. But in fact, freeing, it's a tongue twister. Freeing memory manually isn't free. Try saying that 10 times fast. And even when you don't have garbage collection, if you actually go and you look into the guts of what's happening and you point a profiler at your application, you will find that freeing memory takes time. And so in C, a free call, depending which memory manager you're using, it can take between 8 instructions and something with a mean of 113 instructions. And that's per object that you have to free. So it's not trivial. And if you look at a C application and you figure out what the overhead of the memory management is, how much time is it spending in these calls to malloc and free, for most C applications, it ranges between about 7 and 20%. And if you look at a Java application and see how much time is being spent in garbage collection, it's actually pretty much about the same. And sometimes in a Java application, you get your garbage collection badly tuned and you realize that your application is spending huge amounts of time in garbage collection. But you can actually get the same thing in C. One application that was looked at, the overhead of the malloc and free calls was 53%. So that means the application, even though it didn't have garbage collection, was using over half its time just allocating and freeing memory. So what about when you go to free your memory automatically instead? Well, in fact, when it's well tuned, a garbage collection can have a cost of freeing an object which is less than one instruction per object. And if you think about a free call, no matter how efficient it is, it's going to have to be at least one instruction per thing you free. And so no manual memory management can beat that kind of figure. And the reason for that is that some modern garbage collectors, what they do is there's a cost per object which survives, but every object which is no longer used, which is freed, is free. So what about allocating memory? Again, when you allocate memory, it does take time, no matter what you're using. And allocating memory, it's especially slow if your heap is fragmented, because you've got a free list of all the free chunks, and you want to allocate 100 kilobytes, and you have to look through the free list until you find a chunk which is big enough to accommodate your 100 kilobyte object. And it can also be quite expensive if you've got multiple threads which are all contending. So, you've got 6 threads coming in and they all say, I'd like an object, please. And you've only got one heap. And you don't dare do it concurrently, because then you might get 6 threads all trying to share the same section of the heap. So you have to take a lock and you have to do it sequentially. And that can actually be quite a bottleneck for your application, because the threads are allocating memory continuously. They're always having to go back and do it sequentially on the heap. And garbage collection can help with both of these. And so one of the things garbage collectors do is they compact the heap. And this can help enormously with fragmentation, and it means that the allocation is much faster. And the other thing garbage collection can help with is contention. And so the way modern garbage collectors work is that each thread tends to get a chunk of memory. And so if it's allocating small objects, which of course Java applications tend to do all the time, they don't have to go back and get a heap lock. They can just do it from their little kitty. And if it's a big object, then they can go back to the heap. And this can make things much faster on multi-core boxes. So what about accessing memory? You'll recall when I talked about caches, the order in which you do things does matter. And so not all memory access is equally fast. But garbage collection can really quite speed up your memory access. And if you think about what an application is doing, most of what it's doing is just reading from memory. And so if you make an improvement in this area, it will affect your whole application. And the reason that garbage collection can help improve the speed of accessing memory has to do with what we call locality. And so when an object is loaded into the cache, its neighbors are also loaded into the cache. And so the implication of this is that the relative position of objects, how they're laid out relative to the objects that they call, is really important. And what spatial locality, how many of you have heard of spatial locality? Okay, a few of you. When we say spatial locality, what we mean is the idea that how spatially close in the heap objects are to objects which are accessed at similar times. And if you can improve your spatial locality, your application is going to go much faster. And so what you want to do is you want to try and arrange your heap so that objects which are accessed at around the same time are located near one another. And you think, well, hang on, it's not me that chooses my object layout, it's the garbage collector. So what can I do about it? Well, yeah? What I mean by neighbors is objects which are next to them in the physical heap. So if one has an address 1,000 and the other one has an address 1,100, then they're going to be neighbors. And how you can improve your locality, there's a few ways. One of which is allocating in an unfragmented heap. Another one is when your heap does get fragmented, compacting the heap. And if you think about why this is true, when you've got a cache, you've got this many slots, and you can get that much memory in it. If you've got empty space between your objects in the heap, that empty space is going to get loaded into the cache. And it's never going to be of use because it's empty space. Whereas if you have objects in the cache, then at least, there's at least some chance that the next object you use may already be in the cache. Whereas if the cache is filled with empty space, the next object you use is never going to be in the cache. But in fact, you can do even better than that. And so what modern garbage collectors tend to do is they rearrange objects so that they're near objects they reference. And they can do this by profiling with the JIT, or they can just do this by, if an object references another object, it's likely that it's going to access that object. And so if you put those two objects near each other in the heap, when you rearrange the heap, you're going to improve your spatial locality. Your application is going to go faster. And so obviously, you personally can't do this because you don't control the layout of the heap, but your garbage collector can do this. And being aware of how your garbage collector does it can help you make some good choices. So I'm just going to divert a little bit now to talk about garbage collection strategies. Most JVMs do provide several strategies, again, because all applications are different. And so the default strategy is not necessarily the best in every circumstance. And they differ in a few ways. They differ in how the work is done, what happens to the garbage, and how the heap is laid out. And so the default way to do the work is a stop the world collection. And so all the application threads are paused. And this is the most efficient one. Another way of doing it is incremental. And so collections are divided into smaller collections. You get smaller pauses. Another way of doing it is concurrent. And this is actually usually just a finely divided incremental collection. And so another difference is what happens to garbage. Most classic collectors are a free list collector. And so you search the heap for unreachable objects, and then you add them all to a free list. And then when you allocate a new object, you allocate it from the free list. And when the heap becomes fragmented, which it usually will, and so you'll find it harder and harder to find space in your free list, then you can compact the heap by rearranging your objects. Another way of doing it, sorry, is that a question at the back or just to stretch, okay? Is you can use a copying collector. And what this does is it divides the heap into two. And when you do your collection, you take everything which is reachable in the first half of the heap, and you copy it across to the second half of the heap. And this has the benefit that you're just compacting for free on every collection. And it also has the benefit that the things which aren't reachable, the garbage, you never visit at that area of the heap, you never touch it. And so collecting garbage is free. The downside of this policy is that the stuff which isn't garbage, collecting it is pretty expensive because you have to copy the whole object across. And if it's a big object, then you just end up copying this object from one area of the heap to the other area of the heap and back and forth and back and forth. And sometimes it's not going to be good. And so one strategy for dealing with this is that instead of laying the heap out just as a big area, which is what the simplest collectors do, you divide the heap into generations, because the way Java tends to work is that you allocate a whole bunch of objects, but most of them are just really short-lived and they die quite quickly. But some objects tend to live for quite a long time. And once they've lived for, perhaps 10 garbage collections, it's likely that they're going to live for 20, 30, 40 garbage collections. And so what you do is you divide the heap into a young area and an old area. And in the young area, you use a copying collector and you just keep swapping back and forth. In the old area, you probably don't use a copying collector because you know that what's in that area is large, long-lived objects that are going to survive for quite a long time that you don't want to be just continually copying. And so in the IBM collector, in the old area, we use a concurrent collection policy as well. So you get quite short pauses in the nursery area because it's small. And you get quite short pauses when you do a full collection as well, because it's a concurrent collector. Another kind of halfway between just having a flat heap, which has no structure, and having a generational heap, is cordoning off part of the heap as a large object area. And the reason for this is that when you allocate a large object, if you've got a free list, you probably have to search to the end of that free list to find a chunk of memory which is big enough for your large object. And then as soon as you free that large object, that big chunk in the free list is going to get filled with little objects. And so the next time you allocate a large object, you're going to have another massive search. You may have to compact the heap. It's going to be expensive. It's going to be slow. And so instead, what you do is you reserve part of the heap for large objects. And because only large objects go in that area of the heap is pretty unfragmented, and you can allocate your large objects efficiently. So how does this all relate to what I'm talking about, which is performance myths? Well, one of the things is that we look at garbage collection, you can see that when it's doing garbage collection, the application isn't doing work. And you think, well, obviously, I should try and minimize the time which is spent in garbage collection. Well, sometimes. There's a few things to consider here. One is the distinction between reported work, which you see in your verbose GC, and hidden work. So when you have a concurrent policy, when I first started in performance, I looked at a concurrent policy and I thought, oh, this is going to be great. I'm going to really reduce my application pauses. The application pauses are bad for applications. So I turned on the concurrent policy, I ran my application, and I was quite surprised and distressed to see that my garbage collection pauses were way shorter. I seemed to be spending way less time doing garbage collection, but my application performance was actually much worse. So what's going on? Well, there's still quite a lot of garbage collection work happening. It's just that because it's concurrent with the application, it's not being reported. And in fact, when it's a concurrent algorithm, you usually have to do much more work than you would with a normal stop the world algorithm. And so one of the reasons for this is that you're trying to keep up with what the application is doing. And so if you collect an area of the heap, and you say, I know everything which is referenced from this area. And then the application comes along and very inconsiderately puts in a new reference. Then suddenly, what you think is referenced isn't correct. And so you have to go away. Well, you have to do two things. First of all, you have to trap that right. And you have to say, okay, every time a reference gets written, I need to know about it. And I need to make sure that I update my garbage collection to make sure I haven't just missed something. And then, when the reference does get written, you have to recollect that area of the heap because you know your previous collection has now just been invalidated. And that can be quite expensive. And so when you look at what's actually reported in the pause times, that's only a pretty crude indicator of how much work the garbage collection is actually doing. Another area where it's easy to get confused about pause times is when you look at the mean pause times. And so I've sometimes looked at my garbage collection log and I've thought, I don't want to be bothered to analyze this. I'm just going to quickly look and see, and I see that my pause times have gone down, and I think, oh, good. But in fact, if I'm collecting more frequently, then even though my mean pause has gone down, my total pause and my total overhead on the application could have gone up. And so an easy way to see this for yourself is if you shrink the heap, you'll find that it's faster to collect a smaller heap. Your mean pause will go down. But because it's a smaller heap, you have to collect it a lot more frequently. And so the actual garbage collection overhead is going to go up. And the application performance is going to go down. And we usually try and avoid doing a compaction because they do take so long. And so, if there's a response time critical application, it's going to be horrible. But in fact, even though we were spending so much more time in garbage collection, because our allocation was so much faster, and because the memory access was so much faster, the application actually went faster. Another example is I get emails fairly regularly from customers, and they say, I've changed, and I'm now using a generational collector, and my application's going much faster, and I'm really happy. And I think, oh, good, what I like to hear. And then they say, but I've looked at the verbose GC logs, and I used to be spending 10% of my time in GC, and now I'm spending 30% of my time in GC, and I'm really unhappy about this, and I'm worried, and what should I do? And I email back and I say, this is fine, actually. The generational collector, it does have a higher garbage collection overhead. You will be spending more time in GC with a generational collector, but the benefits of that in terms of your allocation and your access are so worth it that if all you should look at is your application performance. You shouldn't look at these secondary metrics like garbage collection overhead. Just look at the application performance and see if you're happy with that. Another trap we fall into is we think, well, all of this discussion about application performance, that's fine if I only care about throughput. But for my application, what I'm actually concerned about is response times. And so, therefore, the obvious way to optimize this is to try and shorten pause times, right? Well, actually, no. Response times are not the same as pause times. And even actually, when you read academic papers, they sometimes say, and we were trying to make our response times good, so we shortened our pause times and job done. But in fact, sometimes you can get shorter pause times, but actually longer response times. If the application is quite heavily loaded, that's how it will work out. And it has to do with the fact that usually work isn't just coming into the CPU, work has to queue for the CPU. And so if you've got short pause times, but long queues and lots of contention, then you will find that things are actually slower, even though you've got the shorter pause times. So I've got an example here of queuing in a supermarket, which is that if you've got two cashiers and one has quite short breaks, so short pause times, but isn't actually a very efficient cashier, then you may find that you're actually going to get through the supermarket faster if you choose the cashier who takes incredibly long breaks, but is actually quite an efficient cashier. And the same is true for applications. If you choose a queue which has longer pauses, but is actually servicing the application threads faster, you may find that your application response times are faster. Not always, but again, it comes back to measuring. You can't just look at your pause times and try and infer your response times. You have to measure your response times if that's what you care about. Yes?
Would it be better if we have pauses at a predictable time rather than like applying as and when required? Say, like my application, if it is ideal, like it's idle at some time, but it's very busy or CPU intensive work is going on at some time. Like I am really bothered if the CPU intensive work is going on, the garbage collection starts happening. I'm just fine, even if it takes 5 minutes while my computer is idle or my application is sitting, just waiting for some inputs to take. So, yeah, the garbage collection, the pauses are fine, but short and long, they both are fine. If they happen at a predictable time,
Yeah, that's an ongoing area of research. And so one thing that all the vendors are working on is real-time garbage collection and near real-time garbage collection. What IBM has is we've got a technology called Metronome, and it does exactly that. It gives you very predictable garbage collection pauses. Then the other thing that you talked about, people are also looking at, so saying, during this time, I really don't want you to do a garbage collection, but in this time, please go crazy with the garbage collection, compact to the heap, do whatever you like. And that's also something that people are looking at. Yeah, it's a very good point. So when we look at the garbage collector, we think, oh, poor garbage collector. I agree that it's helping me now, but it's doing such a lot of work. And what I'd quite like to do is help the garbage collector. And so one way of helping the garbage collector is perhaps, making sure that you don't hold on to references to objects longer than they're needed. So if you've got a quite large object, perhaps, when you don't need that object anymore, you should null out the reference to it. And in fact, this is a good idea. But when you find yourself nulling out a reference to an object, you think, well, maybe actually I've got the scope of this object wrong. And maybe if I just moved that object from an instance variable to a method variable, that would be better. And you can also take nulling out objects too far. We saw an application once, and they thought, well, I want to make life easier for the garbage collector, so I want to null out my references. And so what they did was they had a finalized method. And so a finalized method is called when the object is no longer required. And so they said, when the object is no longer required, I'll take this and I'll go through, and every reference in that object, I'll set it to null. And unfortunately, this was really not a good idea for a number of reasons. One of which was, when the object is no longer required, all the things it references are going to be freed anyway, so you don't need to go through and manually set them to null. But in fact, it's worse than that, because finalized methods are one of those things which you should just say no to. They seemed like a good idea when they were put into the spec, but in terms of performance, they're almost never a good idea. And the reason is that it's expensive to call finalized methods, and there's no guarantee that a finalized method is going to be called. And so the garbage collector will do everything it can to avoid calling a finalized method. And so if you have all this work which is happening in a finalized method, the garbage collector is going to try and avoid calling that finalized method. So it's actually going to try and avoid collecting that object. And so you thought you were helping the garbage collector, but you actually make life much harder for the garbage collector. And really the best way to help the garbage collector is to code in a conventional style. They're very clever people, the garbage collection people. And what they try and optimize for is normal patterns. And so I think, I'm standing up here and I've got blue hair, and I'm saying you should all be normal. And I think you're probably thinking, she's not normal. She shouldn't be telling me to be normal. But when it comes to your coding, it really is a good idea to be normal. Another example of this, when it comes to helping the garbage collector, is that we think, oh, poor garbage collector, every time I make an object, it creates work for it because it has to be collected, so I should pool my objects. But in fact, this isn't true either, because when you do an object pool and you try and reuse instances of the object, you have to do quite a lot of work to try and make sure that you don't share an instance of the object between two things that think it's a different object. You have to work out how many references are left to that object so you don't accidentally give it out. But the worst thing about object pooling is that the objects that are pooled would naturally be quite short-lived objects, and instead, because they're being reused, they become very long-lived objects. And this, again, isn't normal. And so what generational collectors rely on is the fact that most objects actually die young. And if you're pooling your objects, it means that they're not dying young. Instead, they're living, unnaturally long. And had you just let those objects die, they would have been garbage, and collecting them would have been free. But instead, if you keep them alive, they have to be kept alive by the copying collector, and it has to copy them from one half of the heap to the other half of the heap. And every time you do a collection, these objects that you don't actually even want to keep alive are being copied. And in terms of performance, it's pretty bad. So finally, I'll talk a little bit just about compilation. When we did C development, we compiled, and when we do Java development, instead, things are interpreted at the beginning, and we think, oh, well, I know why it has to be interpreted, that's for platform portability, but wouldn't it be better if I could actually just have compiled Java code? Well, in fact, no. Even, we do provide options to compile your Java code ahead of time, but you won't get stuff which is as fast. And the reason is that dynamic compilation can make optimizations which you just can't do with a static compiler. And so it can predict, based on how the application seems to be running, which branch is likely to be taken. It knows if an interface has multiple possible implementations. And another thing is that when you compile something like C, you say, okay, I'm going to compile for x86. But in fact, there are so many variations in x86 hardware, and some have instructions that aren't possible in others, or they've got a slightly bigger cache or a slightly smaller cache. And so what the JIT can do is it can just-in-time compile to the exact hardware that you're running on it. It can have optimizations for that exact machine, which just isn't possible if you have to try and compile ahead of time. And dynamic compilers can also do conditional optimizations, and so it can speculatively make an optimization. So, for example, if an interface has only one implementation, it's much faster to access than if it has multiple implementations. And so you've got your interface and you've got your implementation, and you've made that optimization. And then some other class gets loaded, and it also implements that interface. And you think, oh no, the just-in-time compiler has made this optimization and it's wrong and everything's going to crash. Well, no, because the just-in-time compiler is smart, and it looks and it says, oh, there's now two things. I better back out that optimization that I made because it's wrong now. And so you get the benefit of the optimization for a while, and then when it's invalid, it gets reversed. And you can't do that kind of thing with a static compiler. There's no way. Another example is when you inline code, it's much faster to run because you don't have to make a separate method call. But you can only inline a method if there's only one implementation of that method. And you sometimes see performance advice which says you should declare all your methods final because that will allow them to be inlined. But in fact, the compiler is smarter than that. You don't need to declare your methods final. If it wants to inline them, it will. And then, if a while later you get 2 implementations of that method, it will just reverse that inlining because it can, because it's dynamic. And then you get the benefit of both worlds. So finally, I'm just going to talk a little bit about Java performance as a whole. I think we all still feel sometimes a little bit that, coding in Java is great, and, you get so many benefits, and it's so much easier than C++. You don't have to worry about dangling pointers and crashes and memory management and compiling and all these things that you did in C. But of course, everybody knows that Java is slower than C++. And, when you do your micro benchmark and you see, okay, let's see how fast we can do this numeric computation, the C++ is faster. But in fact, Java is very fast. I think the reason people think Java is slow is that Java used to be slow, and then the JIT happened, and that just gave such an enormous performance improvement to Java. And so in some cases, C will be faster if it's a very short application. But in so many cases, Java is going to be faster. You get the benefits of the garbage collection, you get the benefits of the just-in-time compiler, and it makes things faster. So to wrap up, what should you take away from today? Well, I hope I've persuaded you that performance is complex, it's hard. And there are no universal truths. Things change, and so you have to look at the performance of your application rather than just going away and reading books on how to make things faster and applying them without thinking. And I've covered quite a lot of myths today. You don't have to memorize each one. The point of this isn't to go away an expert on garbage collection, an expert on dynamic compilation, and an expert on how to traverse your arrays. Instead, when you think about performance, focus on your application and focus on the characteristics that you care about, and don't worry about the rest. So, thank you. Are there any questions?
Hello?
Hi.
Yeah, I have a question regarding Java memory. Like in our application, we have observed that through JConsole that for an application. So it is other than the heap and the non-heap memory which an application uses, JVM internal memory, right?
Yes.
So what's my question?
It's fairly unusual for that to happen. Usually you get memory problems in applications because the application is using too much heap, or perhaps because the application is using native memory, and that might be using too much heap, or too much memory. But it's pretty unusual. The JVM itself doesn't use that much memory. I'd say it was a pretty pathological case if the JVM itself was consuming memory. We sometimes get people phone in and they say, the JVM is leaking memory. And almost always when we actually go and we look, we find that it is the customer application which is leaking memory. It was just a subtle leak that looked like the JVM, but in fact it was the customer application.
Okay, thank you.
Thanks.
Hi, Holly.
I have a question.
Hi.
I had a look at a few code samples in some internet, and I found that GCC compiler has an option to get optimized code, which gives it can probably interpret different patterns and realize that both are do the same task, and creates the same optimized object code, even though both of them, maybe one of them may be very badly written code, but it realizes that both are doing the same thing and generates the same optimized code. Does the Java compiler does anything similar to that?
Yeah, it does loads of optimizations for you. So
this example you gave about the array going through the array to row and column and column and row, doesn't the Java compiler interpret in some way and generate the same object code?
Yeah, that one it won't do. So some optimizations it can do, some optimizations it won't do. So things like methods which have no effect, quite often you'll find those get optimized away. But something like that order in which you do things, usually it will assume there was a reason you did it in that order, and so it won't change that.
And I heard that a switch case is better than if loop in C, at least. Is it different in Java? I'm not sure about that, performance-wise.
I think switch is better, yes. I think, yeah, I wouldn't want to swear to that, but I believe so.
I think in C, sometimes it generates the same object code when you run in the optimal compiling mode. But in Java, I think it doesn't do, because in some forums in Sun, they swear that the switch case are better than the if-else.
Yeah.
Thank you.
Hi, Holly. I have a question here.
Oh, hi.
Thanks for the wonderful presentation.
Thank you.
You talked about heap, structuring it, unstructuring it, and unstructured heap, and having the objects in the neighborhood. So how much control does user has on this heap? Or is it all the control in the JVM, or can user, while creating the objects, can take care of some bits and pieces where he can have the objects in the neighborhood?
It's pretty much all in the control of the garbage collector. It's something to be aware of when choosing a garbage collection policy, to realize that things may become better for you in ways that you didn't anticipate. But in terms of how you write your code, you don't really need to worry about it very much. The JVM will work out which objects reference, or which objects should be near other objects, and it will do that for you. Hiya.
You were talking about the IBM JVM and saying that you thought it was quite superb.
Yeah.
Generally, when you look at the comparisons between Sun and problems, say, with the permanent generation or something like that, the option that most people talk about is JRocket. Are there any specific things that the IBM JVM does that are unique or special or make it superb?
In terms of, there's a few areas where we're very good. One of them is performance, and so for performance, when you look at the benchmark results, it tends to vary on exactly when you look at it, who's on top, and exactly what hardware. But we're near the top usually. And another area where we're very good is in terms of our diagnostics. So our trace is excellent, and the control we give you over the JVM, and in terms of trying to figure out, if something goes wrong with your application, what can the JVM tell you? We're very good in that area as well.
Okay, thanks.
Hi, I have one question.
Yeah.
In case of applications which have some poor memory management and which causes GC to run for a long time, say long pauses, in that case, when GC is actually running, usually the new requests that come to the application server, will they be just left alone, or the server actually will respond to those when the GC is running? Is it totally taking all the control of the application, or still new requests can be served?
If it's a normal stop the world GC, then it will take complete control of the application, and so the application won't be able to respond to anything. And so when it's that kind of web application, you probably do want to choose a policy which isn't going to give you very long pauses. And so in the IBM case, you either want a concurrent policy or you want the generational policy, which does give you pretty short pauses. And so it's going to be better for that kind of case where a response time is required, because when the garbage collection is running, then nothing else happens unless it's concurrent.
Thank you.
Hi, Holly, I have a question. In JDK 1.6, there was a plan to add something called escape analysis.
Oh, yes.
And especially with reference to allocating objects on the stack rather than the heap.
Yeah.
So does it actually work, or has it been implemented?
Let's see. I think every time they do a little bit more on the escape analysis. I think there's still more to be done, but there has been some escape analysis.
I think you need some extra flag to enable it when you run your JVM applications, or does it happen by default?
Most of these optimizations do happen by default. I think, I don't know of an extra flag for escape analysis, certainly.
Thank you.
Hi, Ole. I have a question.
Hiya.
Actually, when you have a collection and you have multiple objects assigned to it, once any of these objects goes out of scope, what does garbage collector do at that point of time? It just goes and, recollect the object from the collection or not?
It should do, yeah. If it's in a collection and it goes out of scope, then that object will get collected.
No.
Oh, sorry.
When the other objects in the collection are in the scope, only one of them goes out of scope. At that point of time, when garbage collector collects these unused objects,
It should, yeah. I think garbage collector will collect it.
if it goes out of scope, then
Yeah.
it will.
Oh. If there's, well, if oh yes, I see what you mean. Yes, in that case, you'd want something like, that's what a weak hash map would be for. You'd want something like that. So, yes, if the collection is still holding a reference to it, then it won't get collected unless that reference is a weak reference. So there's a utility class called weak hash map, which is quite useful for that, or you can explicitly put weak references in.
Okay, thanks.
Thanks.
Yeah. I just wanted to know, like that you suggested that writing a normal application. So can you elaborate upon that? Like, what do you mean by writing a normal application?
Sure. What I mean is that when you do an optimization, quite often it works out that it will make things better half the time and things worse half the time. And so you have to work out whether you're in the case where it makes things better or when it makes things worse. And so what our JIT writers do and our GC writers do is they try and, when they're doing their optimizations, they try and work out what the most common patterns of development are and how the most common applications work. And they try and make sure things are better for those most common applications. And so what that may mean is that things are worse for some other kinds of applications. So with the example of object pooling, it's a common pattern that objects tend to be short-lived, and an object pool will make quite long-lived objects. And so that tends to break the assumptions that garbage collectors make. And so because, the garbage collectors, they look and they think, oh, well, most objects are short-lived, so we're going to try and optimize for the short-lived case, which makes things worse for the long-lived case. And so if you write an object pool, you think you're trying to make things better, but in fact you make things worse. There's other examples to do with the JIT as well. And so if you just write fairly clean, well-structured code, it's going to be readable to you and me, and we're going to look at it and we're going to understand what it's trying to do. And it's also going to be readable to the JIT. The JIT is going to be able to look at it and it's going to be able to say, oh, okay, I get what this code is trying to do. It's trying to do this loop here, and then it's trying to iterate over this, and this object is going to go out of scope here. And because it can understand what the code's doing, it can optimize the code really well. Whereas if you've got some code, that goes around your loop backwards and does all sorts of quite weird things that may be very clever and, may make things better if there wasn't a JIT. Because the JIT looks at it and says, I have no idea what this code is trying to do. I have no idea whether it's most likely to take this loop or that loop, or how many times it's going to go around the loop, or, how often this method's going to be called. Then the JIT's not going to be able to optimize the code well.
Thank you.